Good afternoon, everyone. Welcome back from lunch and from the keynote. I've got a couple of people down from the University of British Columbia. Brad Penoff and Alan Wagner are going to talk to us, along with Mike Tsai, about I always get this acronym wrong, SCTP. It's a transmission control protocol alternative. So an alternative TCP for moving data around our data centers and between them. There are a lot of interesting scalability and reliability trade-offs, and I hope they'll enlighten us on what those are and what they look like. Brad and Alan, you want to?
Hi, thank you. Thanks for coming. My name's Alan Wagner. I'm a faculty member at the University of British Columbia, and we'll do this talk in sort of three acts. Act one, I'll talk about an introduction to the talk. Brad, who's a PhD student at UBC, will come up and talk about some of the details of SCTP. And then I'll come back and talk a little bit about some of what we've applied SCTP to. So this talk's a little bit different maybe in two ways. One, we're coming from a university. So no, I don't have 100,000 machines or 10,000 machines, I'm afraid. And the second thing, I guess, this talk is more going to be at a lower level in the sense that we're going to talk about more from the networking side. Of course, for any machine, there's really the processors, there's really the disks and the I/O, but there's that third part, the networking, and that's what the focus of this talk is. So I think whoops. Whoops. Sorry. So the first question, I guess, has already been answered. What is SCTP? The acronym stands for Stream Control Transmission Protocol. It's an IETF standardized transport protocol for IP. What does that mean? That means basically it sits alongside TCP and UDP as a transport protocol. Okay? It, in fact, can be used in the same way that UDP and TCP can be used. Okay? It's a standardized protocol. It's available. You can go out and read the RFCs for it, and you can download implementations of it. It's a relatively new transport protocol, and it's for reliable, and the keywords here, reliable and message-oriented data transfer. And the third point is that it's really the only reliable IETF standardized protocol that's been introduced in 30 years. I mean, TCP, of course, and UDP have been around for a long time. They all sort of show in their age a little bit, and one of the reasons for SCTP was sort of to address some of those features that you would like to have, say, in a transport protocol. So why should you care? Well, I guess I've said a little bit. There's new features in there, right? New things that you're going to be able. That means new opportunities, new things you can exploit. And the purpose of this talk, of course, is talk about a little bit how it adds or can add robustness and reliability. And some of this comes about because of new challenges that are appearing in the internet. And perhaps one of those challenges are things like multi-homing, where, for example, machines typically these days have multiple IPs, not just one. So hopefully that's why you might be interested in hearing the rest of this talk. Who are we? As I said, there's myself. We have a group at UBC. We've been working for probably 3 or 4 years now. There's myself. There's Brad and Mike, who are here today. Brad's there. Mike's all in the front row. Carl is up. He's working for us for the summer. And Humera, another PhD student, will be joining us again. She was at UBC before. She'll be coming back to do her PhD with us in the fall. I should say that this research is funded by a Cisco University grant and also by the Canadian government through our NSERT. Who are our collaborators? One of our key ones is Randall Stewart. He's from Cisco. He's a co-inventor of SCTP. He's the IETF lead on SCTP, and he, along with Peter Lee, are the main implementers of the stack for FreeBSD and for Cisco. We also work with Peter Lee and Michael, both like Macs. So they've both taken basically the FreeBSD stack and done what is necessary to get that to work in Mac OS X. So if you're on a Macintosh, you can also download and run SCTP. And finally, we work as well with Jana, who's a recent graduate from University of Delaware. University of Delaware also has a number of people who've worked in related areas on SCTP. What are our interests? So, as I said, we're a little bit users of SCTP in the sense our main interest was using SCTP to put SCTP underneath MPI, which is MPI is a message passing interface. It's a standardized, well, people say it's the de facto standard for parallel programming for scientific computation. What that means is, of course, there's lots and lots of programs out there that are written in MPI. Probably some of the largest, well, perhaps you couldn't say on the most machines, but certainly some of the largest, most high performance codes that are out there, in fact, are implemented in MPI. So MPI has been an extremely successful library. What we were interested in doing was seeing how this could run mostly in a wide area network. We looked at implementing, we looked at putting SCTP underneath MPI rather than using TCP, and what would be the potential advantages of that. We've implemented an MPICH2 SCTP channel. What that means now, if you go to Argonne National Labs, you download MPICH2. Our code is contained in that. You can turn on the module and run, if you have the stack turned on, you can run your MPI programs over SCTP. And again, this isn't, you don't have to change your program to do that. We've done the work in the middleware to support it. We're currently supporting a module for OpenMPI. OpenMPI, again, these are both MPICH2 and OpenMPI. They're both open source projects. The OpenMPI is a consortium of companies headed by Cisco, but both of these are open source versions of MPI that you can download, and for the vast majority, I think they're the two most widely used implementations. We also do a lot of testing and evaluating of our programs, of course, and we've done things like task farming and scientific computation, some stuff in bioinformatics. And what we're interested in is seeing how maybe to exploit some of these advantages that we see in SCTP for clusters, and how we can take advantage of it with respect to scalability and in particular fault tolerance. So the rest of this talk really has two goals. The first goal, hopefully, is to introduce you to a little bit of the features of SCTP that you might not be aware of. So I hope that's new material. We haven't, the protocol itself is quite large. There's a number of features. We're just going to focus on the ones that we feel add the most for reliability and fault tolerance. And then we'll come back and I'll talk a little bit about task farming and how we can make use of these features. So let me ask Brad to come up and he'll give the other part of this talk.
Hello, hello. So thanks, Alan. So yeah, as Alan mentioned, I'm going to focus on some of SCTP's features. So it is, in some respects, similar to TCP. It's connection-oriented. It offers services like congestion control and flow control. It's also reliable and available on most major operating systems. But that's not really the focus of what we're going to be talking about here. What we're going to be talking about here is looking at some of the newer features and how it's not like TCP. So these are the 6 that we'll eventually chug through here. The first one that we want to focus on is multi-homing. So first off, what does it mean to be multi-homed? A multi-homed host is a host that has more than one NIC on it. And you might think that that's not happening very often. Well, I mean, in a cluster, it may happen because you'll have your management network, your storage network, et cetera. So in that case, those nodes are multi-homed. I mean, even this laptop that I'm giving the presentation on comes with wireless and standard wired Ethernet. So I mean, it's multi-homed as well. So that's what it means for a host to be multi-homed. in order for a transport protocol to support multi-homing, that just means that the connection between two endpoints is aware of the multiple paths between. So traditionally, when you say connection, you generally are specifying a path too. So in SCTP, they use the term association to talk about the connection between the set of NICs on one endpoint to the set of NICs on another. So now that okay, great, you have multi-homing. What can you actually do with that? How can you use that for some additional fault tolerance? And I'll just walk through a few of the uses. So say you're sending some data upon one of the paths. So we're sending the data across, and for whatever reason, that data is dropped. So in SCTP, alternative paths are used by retransmission. So in other words, retransmissions are passed on the alternative path. So that's more for like a one-off, sort of error. Let's say that maybe we'll have a more catastrophic error in the network, not just a packet dropped here or there. So SCTP, when it's doing its transfers, will initially send all its data upon what it deems to be the primary path. But if like we said, a catastrophe happens in this path, a switch dies or a router goes down, for example, SCTP has the ability to fail over its data transfer. So from then on out, data transfer it has a new primary path, more or less. This happens transparent to the application. So that, anyway, it makes applications in that respect somewhat simpler because they don't have to worry about that, but the transport protocol does. Naturally, since there's multiple independent paths between various endpoints, you might, as an administrator, be thinking, well, I'd like to take advantage of all that bandwidth. There's just a whole other one being wasted there for fault tolerance. So there's been work at the University of Delaware as an extension for SCTP, and not just using the paths for fault tolerance, and failover, but using all of them simultaneously to transfer data paths in between. This is an extension that is actually available on FreeBSD 7 that you can just turn on with a system control command. There's a lot of interesting research issues there with respect to scheduling messages and how it all happens isn't as simple, but as a feature, it's there, and so as a user, you can use it. So that sort of gets us to past multi-homing. A more simpler feature is the fact that SCTP is message-based. So we'll just illustrate what maybe that entails with a really simple example where we have an application where we're sending 3 messages from endpoint Y to X. So yeah, we write, the write system call occurs, and then they're passed through the network, and they arrive in the kernel and they're queued up in the kernel at endpoint X. So in TCP, what happens here, the application asks for the data, read system call occurs. Boom, some data is passed to the application. So what is interesting about this data is that there's no boundary between the messages that were sent, and also you're potentially getting data from future messages. So what this means is that the application itself, it has to be made somewhat more complex because it has to do the message framing. It has to buffer these extra portions. It has to parse data, be it via delimiters or having some knowledge either in data or a priori of size in which to look for these boundaries. So on the contrary, SCTP, like UDP, when a read occurs, the boundaries are actually preserved. So the feature here is that message framing isn't inside the application, and therefore some applications that are not stream-based inherently are simplified because they don't have to do the message framing themselves. A third feature that is interesting in SCTP is their multi-streaming feature. Sort of to motivate this feature, and we'll go first by motivating the feature and then describing the solution and showing it in action. So to motivate this feature, say we're sending the same three messages from Y to X. All these messages are independent. And so we send them across, they're all on the network. And the thing that, a problem occurs. Message A is dropped for whatever reason in the network. We're using commodity switches, say. Okay, so the next two messages are queued up in the kernel. And so let's say the application on X is like, all right, I'm ready. Give me what you got. See, the problem, the head of line blocking problem here, well, this is what head of line blocking is that B and C cannot, even though they're independent of A, even though A, B, and C are all independent of each other, they're made dependent upon each other just because of TCP's semantics. So that's sort of the motivation for this problem. The solution that came up, that the designers of SCTP came up with, was within an association, there are independent streams going, and order is only maintained on a given direction on a given stream. That's the only thing guaranteed. So just to see this in action, say we wanted to send messages A, B, C, D, and E. And our only ordering constraints are that message A has to arrive before C, and C has to arrive before D. That's what the colors are supposed to indicate. So what we can do as an SCTP application developer is put messages A, C, and D on one stream, put B on another stream, put E on another stream. So that's what we do. We send it across, and then, okay, this is where we start to talk about catastrophe. And for whatever reason, once again, in the network, A, B, and C are dropped. So what do you do on the application? As looking at it from X's standpoint, it sees these as three independent streams. But what still happens in SCTP is it can still deliver still deliver message E to the application, thereby avoiding the head of line blocking problem that was present in TCP. So then once A, B, and C are retransmitted, you still can't deliver D to the application until the end. This is because order is only maintained within a particular stream. So on to the fourth feature. The fourth feature has its roots in TCP. It's called selective acknowledgement. It was an extension brought up by Sally Floyd and her team in the early 90s, which, and just to sort of review what that is, so we'll just illustrate it with an example. So say we're sending messages A through E, once again, I like my alphabet. So, and we're going from Y to X, and for whatever reason, every other message is dropped. And so looking at it from what will happen next. So what happens next is, what SAC is SAC is more descriptive. It's able to tell Y exactly what was lost. And so what this means is that when retransmissions occur, the actual number of retransmissions is less. Okay, in this example, it's not as substantially less, but this is a simple example. So that's what SAC is in general. So why is it interesting for SCTP? Like, because, okay, that's present in TCP. I can just turn that on. So how it's unique in SCTP is, well, A, it's built into the protocol. So you don't have to worry about basically implementation-specific issues. It is built into the protocol. Because it is built into the protocol and it's not an extension, when it's implemented in TCP, it's actually implemented in TCP options. That limits, since the TCP header is a certain set of bits, you can only express so many gaps. I think the actual upper bound is expressing 4 gaps. So SCTP can express more gaps than TCP. So like I said, in this simple example, you only express 2. But in more complex examples, it's been shown that, that in high loss situations, more expressiveness in SAC has shown tremendous benefit. So the fifth feature that we'll look at is SCTP's stronger checksum. So like TCP, there is a checksum. So okay, so how's that? So let's break that down. There's several different checksums along the stack, but when you actually when you're looking at the end-to-endness, certain portions of the checksums, like for example Ethernets, is only on a per hop basis. So the only thing guaranteeing your actual end-to-end reliability is TCP's 16-bit checksum. So research has shown that on the order of 1 in 10 million packets arrives corrupted to the endpoint, but passes the checksum, and it's sort of integrated into the data of the application as valid. So you might say, okay, that's not a problem. I have my application. I've never seen this before. Well, yeah, a lot of applications, smaller applications, don't ever run enough to the point where this is observed. But for large-scale applications, this number starts to take on a little bit more meaning. The amount of zeros is important. So the designers of SCTP were given a lot of input from the telephony community, where its roots are primarily from, but also from the I/O community. And in the end, they decided to use a stronger 32-bit checksum called the CRC32C. So on the upside, it's stronger. So, but on the downside, it's also more computationally intensive. Typically, in TCP, we don't have to worry about the computational intensity of a checksum because it's usually available for offload on the NIC. But currently, CRC32C is not commonly available for offload on the NIC. This is changing. There are I/O processors available that do offload this computation. And even if you're not using them, maybe this cost is actually worth it if you're concerned about the reliability of your large-scale data applications. So the final feature that we'll look at is SCTP's choice of socket API. So sort of, it might be deemed as uninteresting, but okay, so SCTP supports something looking like Berkeley sockets. So that just means that if I wanted to write an SCTP program, TCP style, I can do it. If I wanted to write an SCTP program UDP style, I can do it. But probably most interesting is if I already have an application that I want to maybe try out with SCTP, porting it is actually quite simple. All it is changing the parameters to the socket call, more or less. So, but what this will do is it'll give you some of the free features like multi-homing or a stronger checksum. But in order to access some of the more advanced features of SCTP, there is also defined an extended sockets API. So what this does is allow you to utilize newer features like multi-streaming, and then there's also several different socket options that unlock and let you tune various SCTP runtime parameters. So we've walked through so far 6 features. There's several other that we're not really going to go into here. They're just sort of listed here for completeness. So in summary, these are the 6 features that we did review. And in terms of this talk, what's going to happen next is Alan's going to come up, and he's going to discuss how these features can be used in cluster computing. Thanks.
Oh. Thanks, Brad. So let me discuss some of our experience in using it for task farming. I guess task farming, you've heard a lot about it today. It's, of course, an extremely common strategy for work distribution. The picture I have up is a task farm that we've often used. As you can see, actually the task farm, there's a manager on the right. It, of course, creates tasks. It ships them off to workers. Workers work and do all the tasks, and then perhaps the results get returned to some other process. Often when we've implemented processor farms, we actually have the workers request the tasks rather than simply ship all the tasks out to the worker. One of the reasons for doing this is because if you make requests, and if you have a slow worker, then that worker just doesn't get as much and doesn't do as much. So of course, this also known as a map function. You have a function you would like to, some computation. You would like to apply that over a set of data items. Those data items are all independent in the sense that that function could be applied in any order over those data items, and that's, again, as the MapReduce system shows, I mean, that can be a pretty effective way to make use of a lot of processors. But so given this basic setup, let's go back to some of these features that Brad was talking about and see how maybe some aspects of that could help us. One of the things, well, let me back up and just say that, I mean, the best thing that you can hope for in a task farming, I mean, at least one of the main issues, load balancing I don't have up there, that's another one, of course, but is you want to keep everything busy, right? You'd like to get as much work tossed over your shoulder as you can. What does that mean? Well, that means that you're probably going to be buffering tasks inside the workers, so that, minute a worker goes idle, bang, he just, switches buffers and starts working on the next task. You want to have, in our case, we want to have requests going out on the link because, especially if you're using an IP transport protocol, it takes maybe, 80 milliseconds. So you want to make sure you're making requests out there early. You want to make sure that the tasks are flowing in because they might take some time. So you want to basically keep as much stuff active in the system as you can, and that's how you're going to keep those workers really, really busy and there's not going to be any slackers. So this buffering, overlapping, communication, computation. This is where we feel SCTP can help us. So those, again, are the features that Brad talked about. So what about, so let me turn to feature 2 and 6. First, if you look over on the left, requests, tasks, results, these are all messages. And this isn't streaming data. These are basically message passed. The fact that SCTP is a message passed transport protocol helps us in this. It simplifies some things. A lot of people have developed similar type systems using UDP, but if you do that using UDP, you have a choice. Either you're not very friendly in the network, right? Meaning you don't mind swamping everybody, or you end up having to rebuild all the things that TCP have inside your UDP-based application. SCTP's done that. Why do it over again? So that's one thing. Message-based for these type of systems, it was true for MPI as well, it's just more natural. The other thing that's maybe not as obvious, if you go to the one-to-many style of, and that's the UDP-like style of sockets, is, for example, a manager, basically to talk to a lot of workers, only opens up one socket. So it acts like UDP. That is, if a worker wants to send me a message, they just send it to the single socket. Comes in, I read it off the socket, and I do what I have to do with it. Right? What this means is, if you can imagine a system now with many managers and many workers, is you don't have this huge number of sockets that can begin to explode on you. Right? You have, at least in MPI, you sometimes get this sort of n squared. Every processor has to open up n sockets, where n for a large system could be 1,000, 10,000. Or it's opening and closing. It's managing all the state. Right? This simplifies. It simplifies by just having a single socket, or a few sockets if necessary. So that's another advantage. Multi-streaming and selective acts. Again, the picture on the left, Where does multi-streaming help us? Well, again, it helps us remember. We want to throw as much stuff over our shoulder. We want to keep as many requests in the network. We want to keep as many tasks flowing in the network. So, of course, what happens if we lose a request or we lose a task? Well, we don't want to be delayed. We don't want to have that task in front. These are all independent. We want that task behind to be able to jump ahead. So if we arrange things by putting requests and tasks on separate streams, which we do, right? What this means is that if we see a loss, then it's okay. The task coming after will get delivered. So we can keep those buffers full a little bit easier. The other one, and we've done some experiments with this to try to see what the potential saving would be in exactly these types of scenarios. And you do have to, you know, in MPI at least, you have to make sure. I mean, one of the things, of course, you need in a system like that is you need non-blocking communication. You have to be able to do a lot of sends, non-blocking, and you have to be able to do a lot of receives, right, non-blocking in the sense that you're putting out requests, right, receive requests, right? That way things are happening behind you as things come and go. So head-of-line blocking does occur, does help to have things in separate streams. And the other one that, as again, you get basically for free is the SAC processing. And we've seen occasions, and again, this is admittedly in fairly high loss situations, but you can see a huge benefit for the extra SAC processing in SCTP. And it really basically, it punches through when TCP links are in fact dying. Okay, so it's going to go a lot longer and still be able to deliver data when your TCP link would basically be hosed. The last two, multi-homing, stronger checksum, and again, these basically come for free because these are implemented in the transport protocol. Multi-homing, it just adds that additional reliability, right? That means if a path goes down, it's going to reconfigure, it's going to flip over to a backup path, and it's going to continue. You're not going to see the difference. You can, I say that you're not going to see the difference, you can request to see the difference, right? You can get a notification, which isn't a bad thing to get, because if you get the notification that one of your primary paths has failed, that probably means something's going on in the network, and maybe you want to do other things like move some work off of that worker or move some things off that machine. So there is so if you like, it's giving you a little bit of a forewarning of trouble that might happen. Stronger message reliability, I think, you know, Brad sort of told you the basic argument as to why you want stronger reliability if you're pushing around lots of data and you're on large machines and you want things to keep going. So what do we believe? So we believe that if you wanted to, you could go out and you could buy a bunch of small commodity processors. You can go out and buy a bunch of real cheap gigabit NICs, right? Slap a few of them inside a processor. You can go out and buy a bunch of cheap gigabit commodity networking pieces, right? Slap them all together, right? Build a system according to how much money you had. Maybe go out and, you know, pick your favorite parallel algorithm, maybe like search or something like that. Maybe even form a company, maybe even make some money, right? So, and SCTP is going to help. Well, it's going to make things maybe a little bit cheaper. It's going to make things a little bit more effective at the network level. So maybe you don't need to over-provision the network. Maybe you don't have to buy quite as much cheap networking gear. Okay, well, this is a Google scalability, so maybe I should at least mention MapReduce here, right? How might this help MapReduce? Better congestion avoidance, right? If you're using IP switches, you have a lot of machines, you have congestion, right? You have hotspots. No one's going to have the network bisection so large, sufficiently large, that if one half of your machines decide all of a sudden to talk to the other half of your machines, there's going to be some congestion go on. Okay, congestion does happen, and that's of course where you get loss, right? That's where things like SAC's going to come into play, head-of-line blocking, all these other techniques. SCTP, we didn't talk about this, but I noticed, at least in the MapReduce paper, that you know, MapReduce uses heartbeats between workers. I just wanted to mention as well that SCTP, I mean, one of the ways it knows whether or not a link fails or not is it has a heartbeat system between the either ends of the association. So it actually has a mechanism to ensure that things are up and going. Again, you might not have to recreate that again at the higher level. Another perhaps more subtle thing that we investigated is that, there's something that happens in processor farms that actually I noticed quite a long time ago when we were doing some other work, and I think it came up here as well, is that, when things are sort of at the end, in the sense that, sort of the end game of processor farm where you want things to be finished as soon as possible. One of the good things, of course, to do that is you don't want to have some worker out there who's basically overloaded, right? Has huge buffers, and everyone else is finishing, and he's got piles of work left to do, right? Of course, that means it's not going to finish on time. So if you're a little bit smarter, you can do things like try to reduce the buffers. Reducing the buffers as well means that you'd like to get by, in some instances, you'd like to reduce those buffers so you can use as little buffering as possible, right? Little state's good, right? Make those buffers as small as possible. And I think some of the things in SCTP, like its SAC processing, it means we see at least try to minimize, and I'll call it jitter, for lack of a better word, is that means just how much delay there is between when the tasks are coming in. Because of course, if we have huge delay, then we run the risk of our buffer running out, and then of course, the worker won't be working, terrible thing, right? So we hope that, but of course, if you make your buffers too large, there's the possibility that there's too much work, and that one's going to end up delaying you in the end. So it's nice to be able to perhaps sort of, reduce what I'll call jitter. Conclusion. So, I hope, and one of the primary reasons for this talk is I hope I've encouraged you to take a look at this. This is all software. You can go download, look at all the source. You can change to your heart's desire. SCTP is available on most OSs, as Brad said. Probably the most feature-rich one is the one that Randall produces, the KME stack. It's again freely downloadable. It's going to become, it's part of FreeBSD 7. You'll maybe have to turn it on. It's part of Linux as an experimental stack. You have to turn it, if you want to turn it on. There's Solaris versions of it. And as I said, the Mac OS one is basically the FreeBSD one. If you want, and I hope I've encouraged you to find out a little bit more about this, you can go to Randall's site at sctp.org. You can go to a Michael Tuxen's site in Germany. There you'll get the Mac OS version of it. As I said, we have implemented this in MPitch too, so you can take your MPI programs, or you can write your MPI programs. You can download MPitch 2 from Oregon National Labs. You can turn on the SCTP, and it will work there as well. And finally, there's a link to our papers and projects that we've done over the years on SCTP. And so I really encourage you, as I said, download it, try it out. It's pretty basic clustering tools. Thank you very much, and if you want to find us, Google us at SCTP MPI. Thank you.
We've got a few minutes for questions, if anyone has any. You want to?
Well, let's.
So,
do you know of any either commercial or large-scale implementations which use SCTP?
Yeah. So let me mention. I mean, I don't work for Cisco, so I don't know. But Randall works for Cisco, and SCTP is in the Cisco's iOS. So it's in all their router products, and it's used. I believe it's used as part of their data centers. So yeah, this is a serious technology that Cisco has certainly been developing and supporting over the last 4 or 5 years. And
I'll just add one thing. Since its roots are from telephony, it's also a part of this SS7. I don't know exactly what it is, but it's a standard for voice over IP
and call admission. And it's been adapted by the IETF for the SIGTRAN group as well, which is a signaling group.
My question is, Well, it gets back to TCP. You've been talking a lot about congestion avoidance, right? And so if I have a lossy line, the SACs help, other things help. But the real problem I've seen with TCP is as soon as you get up to speed, you get to 60 miles an hour, you hit a little road bump and you get that slow start you back down to. How do you deal with that?
Well, so there's SCTP didn't recreate the. Well, let me say, SCTP basically uses the same congestion control mechanism as TCP. So there's no new invention there or no new insight inside SCTP for congestion control. And having said that, the same problems with TCP also would be true for SCTP, and as well, the same solutions that people have been investigating with TCP will also can be applied in a straightforward manner to SCTP. Now, there are a few places where this changes a little bit, and particularly this gets to things like the concurrent multipath. There, things become a little bit more interesting in terms of congestion control. And I should mention that SCTP is sort of entirely friendly in that sense, right? So unlike UDP, it won't hog out a link, right? It will basically share the link among all the different streams and things, or SCTP sessions.
I actually have two questions. Over here, sorry.
Yeah, so thank you.
When you set up these multipath channels between two applications, how do you, think they were called associations. How do you associate, is it done at the application level to sort of declare that these 5 IP addresses are actually one host? How are those associations maintained?
So in SCTP, so the call is the same as in TCP, right? You open up a socket and you bind to it. By default, what happens when you bind to it, you will actually get all the interfaces on the machine. So by default, it will open up, it will create one of those multi-end to multi-end associations. Now there is a special call called bindX, which allows you to sort of selectively pick which ones you want to be as part of that association. So you can, so there's a way to do either, if you like. But by default, what you get is all of them.
And then the other question that we're sort of interested in is any idea when Windows would ever adopt?
I would love to know.
Because everything on one end of our connections is Linux.
Yeah.
Everything on the other end is Windows.
Yeah, maybe there's somebody from Microsoft who could say when when Windows could implement this. I should say that there is a project that a person did at the University of Delaware, which in fact I think creates a little shim layer that will, in fact, I believe, let a TCP connection, SCTP connection talk to a TCP connection or switch. So I'm not absolutely sure about that, but yeah, absolutely. I mean, like any new protocol, I mean, the big question here is, of course, how do you get widespread adoption? And it's a classic chicken and egg problem, right? It's not going to be adopted until more people use it, and more people aren't going to use it until it's widely adopted. So it's always that problem.
So we'll take one more question, and then afterward, if you want to talk to Brad or Mike or Alan, I'm sure they'll be available over coffee.
Hi, I was wondering if there's any allowance in the multiple links with the association to try to avoid the thundering herd problem that you get sometimes. So if you're sending an RPC out to like 50 machines, if they're doing similar tasks, they're going to respond at about the same time, and you'll tend to overflow the buffer on your switch and drop packets and stuff like that. And so is there any allowance in there to try to randomize which link it goes over to try to cut that damage down?
Interesting question. I mean, again, I think once you go, I mean, the initial SCTP proposal, of course, used this in a very simple way, right? Simply as primary and failover. But you're absolutely right. I mean, and in fact, Jana's work at Delaware, when he looked at concurrent multipath, just looked at basically trying to share the bandwidth as best. But you're quite right. I mean, you could think of other ways that you might want to be a little bit more clever as to how you could schedule paths like that, right? So it's an interesting question.
All right, let's thank the speakers one more time.